Welcome back to statistics. We know that the sampling distribution of a sample mean tends to become more normal, especially as the sample size gets larger. We also know a little bit now about how to work with the normal distribution to calculate areas under the curve and the proportions that they represent. So now we want to put those two ideas together and begin using the normal distribution to actually work quantitatively with sampling distributions and say definite things about them. So working with sampling distributions with the normal approximation. The first thing we need to discuss is when is it valid to use a normal approximation for a sampling distribution. There's really two cases here. One we haven't really talked about before, but I think it will make sense. We know that sampling distributions tend to make a normal shape. So it makes some sense that if the population distribution is normal to begin with, then the sampling distributions will all be normal, no matter what the sample size. And that's in fact true. Here, for instance, is a population distribution on the left consisting of body temperature readings, mean of 98.3, a standard deviation of 0.8 in degrees Fahrenheit. And on the right, you see the sampling distribution for samples of even the smallest possible size, n equal 2. And you see that characteristic normal shape. So if, sampling distributions tend to be normal in shape no matter what the population distribution, it makes sense that they'll be exactly normal in shape if the population distribution itself is exactly normal. Now notice this doesn't mean the sampling distribution is the same as the population distribution. It just has the same shape. The standard deviation of the sampling distribution we know is different than the standard deviation in the population, and you see that reflected here. In the population, the standard deviation is 0.8 degrees, but in the sampling distribution, it's going to be the population standard deviation divided by the square root of the sample size. And that turns out to be 0.5657 here. So the two distributions are normal, but they don't necessarily have the same means or standard deviations. The second case, when it's valid to use a normal approximation for the sampling distribution, occurs when the sample size is just large enough so that for almost any population distribution, the sampling distribution has become normal. And that occurs most cases, in almost every case, that'll occur by the time the sample is of size 30 or larger. So here, for instance, you see a trimodal population distribution, but looking on the right, the sampling distribution of X bar, when the sample size is 30, has become essentially normal in shape now. So there are really two main cases for when we can use the normal approximation for a sampling distribution. The first is when the population distribution is itself normal. Then you can use the normal distribution for any sample size. The second occurs when the population distribution is not normal. And in any of those cases, pretty much a sample size of 30 or more will be sufficient to guarantee that the sampling distribution of X bar is approximately normal, and we can use that approximation in our calculations. So let's look at a couple of examples. My examples deal with this scenario that came out in 2019 when researchers estimated that the average time U.S. 8 to 12-year-olds spend viewing screen media, that would include television, phones, tablets, and so on, is 4.5 hours, with a standard deviation of 1.8 hours. And this does not include time spent doing schoolwork on computers or tablets and so on. So suppose we take random samples of size n equal 36. How would we describe the sampling distribution of the sample means x bar? Well, we're not given any information about the population distribution except that it has a mean of 4.5 and a standard deviation of 1.8. But we do know that the samples we're taking are of size 36. So we do in fact know that the sample size is at least 30, and so when talking about the sampling distributions, we can assert that the sampling distribution of x bar is going to be approximately normal because it meets that condition that the sample size is at least 30. So to describe the distribution in detail, we need to describe its mean and its standard deviation. Now, the population parameters, the parameters that describe individual 8 to 12-year-olds, are that the mean viewing time is 4.5 for an individual, and the standard deviation is 1.8 hours. So screen viewing time varies with a standard deviation of 1.8 hours from individual 8 to 12-year-old to 8 to 12-year-old in the population. What about the sample means, though? Well, there we use the properties we know for sampling distributions. That is, the mean of the x bars is going to be the same as the mean in the population, so that's 4.5. And the standard deviation of the x bars is going to be the standard deviation in the population divided by the square root of the sample size. So that's where we get the 1.8 divided by the square root of 36, which turns out to be 0.3. So we can summarize all this nicely by saying that the sampling distribution of x bar is approximately normal with a mean of 4.5 and a standard deviation of 0.3. Let's use this information to answer some questions about the sampling distribution. How likely, for instance, would it be to obtain an x bar, a sample average, of 5 hours or more if the mean screen time today hasn't changed since the research was published in 2019? So to answer that, we look at the sampling distribution of the sample means, which we now can describe as normal with a mean of 4.5 and a standard deviation of 0.3. We're looking at x bar values that are at least 5.0, and so I've highlighted those in the graph there. There you see the area corresponding to x bar values of 5.0 or more. And using software, we can calculate that the probability of those x bars is 0.04779. And so we can say that a sample mean of 5.0 or larger would be somewhat unlikely, a probability of about 5%, right, actually a little bit less, if the true population mean were indeed still that 4.5 hours that was reported in 2019. So 5.0 would be kind of atypical for a sample average in this distribution. A second example continues with this same scenario. So we're still looking at screen times for 8 to 12-year-olds. Suppose that a magnet school implemented a program to limit screen time among its students. Later on, to see if it's working, they survey an SRS of 36 of their 8 to 12-year-olds about their screen time. And suppose that in the sample average, they found that 4.3 was the sample average. So among these 36 that they sampled from their school, the sample average was 4.3 hours of screen time per day. How strong is this as evidence that the school's program to limit screen time is working? Well, you could certainly say that it's evidence in favor of the idea that the program is working, right? Because now their screen time is less than 4.5 hours. It's 4.3 hours. But the question is, how strong is that evidence? Because, look, a skeptic could argue like this. They could say, well, look, yeah, you took a SRS, so that's good, a simple random sample of size 36, so it's probably representative. But that average of 4.3 that you saw could be just bad luck, right? You could have just sort of like, through luck of the draw, had an overrepresentation of students in the sample who spent less time on their tablets and phones than average. And that could explain why the sample average was 4.3, even if, the true mean in the school were still 4.5. In other words, even if the program weren't working at all, you might still see a sample average of 4.3 or less just through random luck of the draw. So how could you quantify this sort of argument? Well, one idea is as follows. If the school's program were actually working, and you compared that 4.3 to what would be typical in the country at large, right? In the sampling distribution centered at 4.5, that 4.3 would be atypical. It should be atypical and far to the left. Is that actually what's happening? Well, here you see the sampling distribution, assuming that essentially the program isn't working, right? Assuming that the magnet schools program isn't working, the sampling distribution would still be centered at 4.5. And then ask, well, is 4.3 really atypical in that situation? And the answer is no, right? 4.3 is pretty close to the center of that distribution. In fact, sample averages of 4.3 or less would occur with a fairly high probability, and I've calculated it here. It's the area of that shaded region. It's about 25%, 25.25%. So a sample mean of 4.3 or smaller would be fairly typical, even if the program weren't working at all, right? Even if the true mean were still 4.5. And so the data that your sample mean was 4.3 does not really provide strong evidence that the true mean screen time at the school, among all students at the school, is less than 4.5, simply because a sample average of 4.3 just wouldn't be that unusual, even if your program didn't move the needle at all, right? Even if your program did not change behavior at all, you still wouldn't be surprised to see a sample mean of 4.3. So this kind of logic is actually foreshadowing some of the logic and inferential statistics that we will be increasingly taking a look at and examining. But right now, I just wanted to sort of use it as a way to show how we can use our normal distribution calculations to say definite quantitative things about the sampling distribution of X bar. We'll continue along these lines in a subsequent video. In the meantime, y'all take care, be safe, and I will see you next time.